Greeting coding enthusiasts, welcome back to this channel. Today let's solve another LeetCode problem, sum of distances in tree. This is a pretty good problem and the hard one too, but don't worry, we'll make this easy. This problem asks us to find the sum of distances between a node and all other nodes. Let's see an example. Suppose we are given this graph, and let's first calculate sum of distances between the node 0 and all other nodes. The distance between node 0 to itself will be 0, and 0 to 1 it will be 1, and then 0 to 2 it will be 1 again, and then 0 to 3 it will be 2, and 0 to 4 again it will be 2, and then finally 0 to 5 it will be 2. So the sum of distances, let's call it SD, will be 1 plus 1 plus 2 and 2. Okay, the total it will be 2. Similarly, if we calculate distance between the node 1 and all other nodes, distance between the node 1 and itself will be 0, and 1 and 0 will be 1, 1 and 2 will be 2, and 1 and 3 it will be 3. Similarly, here also it will be 3, and here also it will be 3. So total sum of distances will be 0 plus 1 plus 2 plus 3 plus 3 plus 3. So total it will be 12. Let's do one more for the node 2, that is calculate distances between the node 2 and all other nodes. Again, the distance between node 2 and itself will be 0, and all these nodes 0, 3 and 4 and 5 will be 1, and between 2 to 1 it will be 0. So sum of distances will be 0 plus 4 times 1s plus 2. So total it will be 6. In the same way, we need to calculate sum of distances for each individual node in the given tree. Now, the brute force approach is to run DFS from each node and calculate distances to all other nodes, and the time complexity for this brute force approach will be order of n into n, that is order of n square. One for DFS to run on each node, and another for to calculate distances to all other nodes. Okay, with the given constraint, our brute force is not going to work. Also, I'm not going to implement this brute force solution, but will provide you the code. Now let's see a better approach for this. Let's see a few observations. Whenever we calculate sum of distances between a node X and all other nodes, we treat that node X if it was a root of the tree. Now it's time to figure out what happens when we transit from a node to other nodes, that is from parent node to child node. Suppose we are given this graph, and if we calculate sum of distances for the root node, that is node 0, it will be 13. Now if we go to the child node 2 and calculate sum of distances for it, it will be 13. Unfortunately for both the nodes, sum of distances came out to be true, but that's not the point here. Now please notice the transition here. Distances of all the node in the subtree 2 are reduced by 1, and distances of parent node, that is parent node of node 2, in this case it is 0, and all other subtree are increased by 1. Again, distances of all the nodes in the subtree 2 have decreased by 1, while the current node and all other subtrees nodes have increased by 1. We can leverage these characteristics to calculate the sum of distances for child nodes. Let's see how. Initially, we calculate size of our subtrees and distances of our nodes by rooting it at node 0. So let's say size of our this subtree is S2. Okay, and we can then calculate number of nodes in this subtree encircled by green. It will be we know the total number of nodes, and if we subtract the size of our subtree, then we will have the number of rest nodes. Okay, so using this information, we can calculate SD for that is a sum of distances for our node 2. We know the sum of distances for our parent node, and we decrease the number of nodes whose distances have decreased by 1, that is S2 size of subtree, and we add the number of nodes whose distances have increased by 1, that is n minus s2. Okay, that's it. So in general, if we are at node u and we are going to a child node v, so sum of distances for v will be sum of distances u minus of subtree of v plus n minus subtree of v. Okay, let's do one more example for better understanding. Now we are at node 2, came from node 0 and want to go to child node 5. Okay, again, distances of all the nodes in the child subtree we are going to have decreased by 1, while parent nodes and other subtrees have increased by 1. Okay, again, we calculate sum of distances for the node 5 by sum of distances of its parent node, that is in this case it is 2, and then we subtract number of nodes whose distances have decreased by 1, that in this case this is number of nodes that is in the subtree of 5, and then we add rest of the nodes by 1 whose distances have increased by 1, that is n minus s5. Okay, so finally let's finalize all of the observations. First, we're going to root our tree by some node, let's say node 0, and then calculate distances of all other nodes and size of our subtree, given that our tree is rooted at 0. And our next step is to calculate sum of distances for our root node, and our final step will be, as you go to our child node v from u, we calculate sum of distances for the child node using below relations, and that would be st, as we already discussed, st of our current node minus size of our v subtree plus we add rest of our nodes, that will be n minus sv. Okay, so let's implement this approach and see it in action. I have already prepared our adjacency list to save us some time, so we'll start writing by DFS function, which calculates distance of a node from our root node and size of our subtree. This DFS function is going to require our adjacency list and our current node, let's call it u, and its parent node, let's call it v, and the two vectors, one for distances and one for size of our subtree. Initially, size of our subtree will be 1, the node u itself, so we'll set it to 1, and then we'll iterate through each of the child node. Now we're going to calculate distance of our child node v, that would be distance of our current node plus 1, and then we'll make a DFS call to our child node and we'll pass all the required parameters. V will be our current node and parent will be our u node, d and s. Similarly, we'll calculate size of our subtree, that is u, and it will be this one. Okay, now execution of these 3 lines does matter. Why? Because we calculate distance of our child node while going down the tree, and we calculate size of our subtree u when we know the size of our child. This is all required in our DFS functions. So let's invoke this function down the code. For that, we are going to declare 2 vectors, one for distances, one for size of our subtree. Now we are going to invoke our DFS function u, and initially the parent of our root node will be -1, and other things 2 vectors d and s. Okay, now first of all, we are going to calculate sum of distances for our current node, that is our root node 0. So for that, I am going to declare a variable and call it st, which is sum of distances. Initialize it 0 and iterate through all the distances. and it will be simply sum of all of it. Okay, and next we are going to require a vector to store our answer. We are going to require another DFS function which computes sum of distances for each node in the tree, and I'm going to simply call it DFS2, and this will require our adjacency list, our current node u again, and then our parent node it should be 0, and our parent node of our current node would be -1, then sum of distances for our root node and size of our subtree vector, and finally answer. And we also need to pass a number of nodes in the tree, that is n, which is already given to us. So let's write this DFS2 function quickly. These are all parameters we are going to need in the DFS functions. Now this SD value, that is sum of distances, is currently for our current node u. Okay, so we'll set it to set it in our answer vector, that will be SD, and then we are going to iterate through each of the child again, and then we'll calculate sum of distances for the child node v using the relation we already discussed. That let's call it SDV, and then it would be SD minus number of nodes whose distances have decreased by 1. It would be subtree of v plus number of nodes whose distances have increased by 1, and it would be n minus subtree size of v. Okay, and after that we will make a call for child node. It should be current node v and parent node u, and our sum of distances for our v will be SDV and s and answer. That's all. Now finally we have to return our answer vector. Okay, that's all the code we need. Let's run this. Okay, something we didn't pass, I think. Oh, we forgot to pass our n value, so let's run it again. One more error. Oops, it should be initially it should be 0, not u actually. So let's run it again. Okay, now it seems our sample test cases are running fine, so let's submit it. Yeah, our solution is accepted. Let's quickly discuss about time complexity of this algorithm. All of these are DFS functions are running on order of n time complexity, so overall time complexity of this approach will be order of n only. Okay, thanks for watching. If you enjoyed this solution, leave a like and subscribe to this channel for more problem breakdowns.